So the idea of this podcast is to give you some feedback on your mastery of dimensional analysis, and it's comprised of 3 questions, and what I suggest you do is write the questions down on paper, have a go at them, and then afterwards you can look at how the rest of the podcast continues and you can see the answers. So here's the first question. Density is defined in this way. What are the dimensions of density? The second one is about Young's modulus, defined through this equation. The terms are defined here. Find the dimensions of Young's modulus. And the third question uses calculus, and this is the time-dependent Schrodinger equation. The various terms are defined here, and the question asks you to find the dimensions of Planck's constant, or the reduced Planck's constant, as h bar is called. So have a go at them and then come back and see if you've got them right. So with that, I'll pause. Okay, welcome back. So the answers now follow. So on this slide, I've written out the answers for the 3 questions, and if you've got them right, that's very good. And if you'd like to see the solutions, or you've not been able to do one of them, the answers, detailed answers, are on the following slides. So with that, let's go on to the answer to the first question. So here I've written out the answer. Density is defined as the mass divided by the volume that it is contained in, and the dimensions of density are therefore going to be the dimensions of mass over volume, which means it's the dimensions of mass over the dimensions of volume. Mass is mass, so the dimensions are mass, capital M. So little m is the symbol for mass, capital M is the symbol representing the dimension of mass. V, a volume, is always made up of a product of 3 lengths. So the units, for example, in SI units are meters cubed. So the dimensions of volume are length times length times length, length cubed. That means that the dimensions of density are m, capital M, divided by L cubed, as written here. And using the rules for powers, I'll write that as mL to the minus 3. So that was the answer to the first question. Let's now look at the second. So, Young's modulus, which I'm representing as capital E, is something which is used in physics and engineering, and it's defined through a force multiplied by a length, divided by an area, and also divided by another length. And the sort of situation it occurs in is that you have something like a piece of metal of length L and cross-sectional area A, and you apply a force to it and it stretches, or it could compress, and the length changes from L to L plus X, so X is the extension. So F is a force. We remember one of Newton's laws, F is ma, so the dimensions of force are the dimensions of mass times the dimensions of acceleration. These are things that I think one should know off by heart. The dimensions of mass are capital M, and acceleration has dimensions Lt to the minus 2. So now we have the dimensions here. L is a length, so it has dimensions capital L. A is an area, so it's going to have dimensions of length squared. Any formula for an area involves a length multiplied by a length. X is an extension, it is therefore also a length, and it has dimensions of L, capital L. So the dimensions of Young's modulus are going to be the dimensions of force times the dimensions of little l, divided by the dimensions of area, and also divided by the dimensions of the extension. So it's mLt to the minus 2 from the force, and times capital L for the dimensions of length, divided by length squared for the area, and divided by length for the extension. So you can see immediately that these factors here will cancel, and we have mLt to the minus 2 over L squared. That also, by the way, gives us the SI units immediately for Young's modulus. This, remember, is a force. This is an area, so it's force over area. It's going to have the units of pressure, which are Pascal. But in terms of dimensions, L over L squared is, from the rules for powers, L to the minus 1. So it's m times L to the minus 1 times t to the minus 2. And these are the dimensions of Young's modulus. So again, it's just a matter of breaking it up into bits, multiplying together using the rules for powers and simplifying. And with that, we'll move on to the third exercise. So in the final exercise, we have a differential equation, and we're asked to find the dimension of this quantity, which we read as h bar. It's written as h with a little line through it, and it's called the reduced Planck's constant. So I is a number. It is the square root of minus 1, and it is dimensionless. T is time, and psi is a wave function. Now we notice that psi occurs here and here. That will be very important in a moment. The other thing to realise is that if you differentiate a quantity, here psi, with respect to something, in this case time, what you do is you reduce the dimension of this by 1 power of the dimension here. So this means that the dimension of d psi dt is going to be the dimension of the wave function psi divided by capital T, the dimension of time. And that is something which follows from thinking about the basic definition of what a derivative is. This derivative, you can obtain it as a limit of a difference of the wave function, which is going to have dimension of the wave function, divided by a difference of, in this case, times, which is going to have dimension of time. So that's very important. Now, we're going to you might have thought when you looked at this, first of all, I don't know the dimension of the wave function, but because it's on both sides, that doesn't matter. This is a general point that matters a lot. So the dimension of the left-hand side is going to be equal to the dimension of the right-hand side. I does not have a dimension, h bar does. We want to find it. As we've discussed here, we can replace the dimensions of this by the dimensions of the wave function divided by capital T, the dimension of time, and on this side, just factorising this, we have the dimensions of energy times the dimension of psi. And so we see that on both sides we have dimensions of psi, and that means that they will cancel. So what we realise is that the dimension of h bar is going to be the dimension of energy, and then we multiply both sides by t to bring this to here, so it's going to be multiplied by the dimensions of time. E is energy. We know various expressions for energy, such as a half mv squared or mgh, and from any of these expressions we see the dimensions of energy. Let's look at this one, are the dimensions of a half mv squared. A half is just a geometric number. M has dimensions of mass, and V has dimensions of Lt to the minus 1. V is the speed, and when you square it, you're going to get L squared, and then T to the minus 2. So this is the dimensions of energy. We put that back into our equation for the dimensions of H, multiply it by T, so we have T to the minus 2 times T. They partly cancel, and we have mL squared T to the minus 1. And those are the dimensions of the reduced Planck's constant. And if you were to think about it in terms of the SI units, well, this is energy and this is time, so it's going to have units of of energy times time, so it would be joule seconds. But the more abstract way of thinking about it, the more general way of thinking about it, is in terms of dimensions, and these are its dimensions. So the important thing to realise here for calculus is that if you're differentiating something with respect to a quantity, the dimensions of the derivative are the dimensions of what was being differentiated divided by the dimensions of this quantity, in this case time. And with that, I will stop this podcast.